similar to our previous two sections, we're still going to be looking at systems of equations. Our first section of this chapter, we were looking at systems of equations in 2 variables. Then we thought about systems of equations in 3 variables. And the new thing that we add to this section is nonlinear equations, so not just straight lines. This can include things like parabolas, circles, any shape of graph like that, and then also inequalities. Now, if we have a system of equations where one or more of the equations is nonlinear, by that we mean not a straight line, then there's a few cases. You could have a case where there are still no solutions. In this case, the nonlinear equation and the line would just never intersect at any point along the plane. We could have one solution if this is a parabola. The parabola and the line could meet at a single point, only there, and then never meet again. And this is one thing that these figures are just showing the idea of a parabola and a line, what could happen. And a parabola, you're going to recognize that it's going to be something that involves an x squared term. Or we could have that the parabola and line would intersect each other only twice. And for a parabola and line, there are no other options except for none, once, or twice. There's no way that a parabola and a line can intersect each other more than 2 times. So these are our visual options. But if instead we were looking at a circle and a line, then imagine a circle and a line graphed in the same axis. They could have no solution, in which case they never intersect each other. One solution where they intersect at only one point, or 2 solution where the line passes through the circle. The other thing that we would like to consider is what would happen if we had a circle and an ellipse. Now an ellipse is just imagine like a bent circle. It's a little more oval shape. Well, one thing that could occur is that the circle and the oval could be inscribed in each other. We know solutions of the equations are where they intersect, so since these would never intersect, this would be no solution. We could have one solution wherever they intersect each other at a single point. They could intersect in 2 locations. They could intersect in 3. And then finally, possibly in 4. So that's just a visual identification of how many different possibilities there could be for solutions of a system of a parabola and a line, a circle and a line, a circle and an ellipse. Now, how would we go about graphing a nonlinear inequality? Let's quickly just review the inequality symbols. This symbol should be read as y is greater than x squared minus 4. This should be read as y is greater than or equal to. Notice the extra line here is the or equal to. And I always remember that the smaller part of the angle points to the smaller section, the bigger part of the angle points to the bigger number, so that's why we'd say y is greater than or equal to x squared minus 4. And the distinction between a and b is it's still y is greater than this equation, y is greater than this equation, but graphically the way we distinguish strictly greater and greater than or equal to is if it's strictly greater, it has to be a dotted line, and if it's greater than or equal to, it's a solid curve. Now the next one should be read as y is less than or equal to x squared minus 4, y is less than or equal to. The distinction between c and d is just less than is dotted line, less than or equal to is solid. And now let's compare the graph of A and the graph of C. Now both of these inequalities dealt with the same equation, x squared minus 4, x squared minus 4. But if we were shading when is y greater than x squared minus 4, remember that this curve traces out when is y exactly equal to x squared minus 4. So if we want to have y values greater than those that are defined by this curve, we would want to be above it, which is why we shade this section. Similarly, if we wanted to be y values less than those that are equal to this curve, we would need to be below that. which is why we would shade outside. We're also going to discuss another method of how to determine where to shade, but that could be the visual one is thinking if it's greater than, we need to shade above the curve, if it's less than, below the curve. So now we're going to graph our own inequality, and I'll mention another method to identify where do you shade, what part of the inequality. First, we need to think about how would you graph, this is y is greater than x squared plus 1, but before you can graph the inequality, you first have to understand the equation. What does y equal to x squared plus 1 look like? First, we would make a table of values, and in this case, you'd want to choose some x values before and after 0, equally spaced, so let's say maybe -2, -1, 0, 1, and then 2. So to evaluate this, I'd say -2 squared plus 1, that's going to be 4 plus 1, that would be the y value of 5. -1 squared plus 1, that's going to be 1 plus 1 is 2. So we're plugging in the points. 0 squared plus 1 is 1. 1 squared plus 1 is again 2. 2 squared plus 1 is 5. So we've got these xy points. Next, let's plot them. So we'd go 1, 2, 0, 1, 2, and we need to go up to 5. Let's add a line up here at 5. And we plot the points. We've got 0, 1. Next comes -1, 2, -2, 5, 1, 2, 2, 5. Now, since this is strictly greater than, there's no or equal to, we would connect these with a dotted curve. So we know this would look something like a parabola. So these are enough points to give us the general shape, and then we do dotted because it's not equal to. And would we agree that this curve splits the x and y axis into two sections, those above the curve and those below the curve? So this is important. We need to visualize that this separates us into two distinct sections. So what's outside of the line and what's inside the line. We need to determine which of those we should shade. Now, you can think about it in terms of understanding the inequality. I'm going to illustrate that, and then we'll illustrate a different method. I would read this as y values should be greater than those values that are on the curve. Now, these are the values on the curve, and the y values need to be greater than that. The y is the vertical axis. When are y values greater than this curve? When it's above the curve. Had we shaded in below, then that would be below it, which would be it's not greater. So that's one way that you can know that you should shade above. Another way is that you can pick a point that's clearly in one of the sections, and specifically, unless this part is taken from the curve is on it. For instance, do we see the point 0, 0 is not on the curve? And the reason we like 0, 0 if it's available is it's a very nice equation to work with. So you pick a point in one of the sections, and you plug that into the inequality. If you get a true statement, that means you should say shade the part of the graph that includes that point. But if you get a false statement, then you should shade the opposite. So plugging 0, 0 in, that's saying when y is 0, x should be 0, and let's see if this is true. 0 is greater than 0 plus 1. Is 0 greater than the word positive 1? This is false. That's not true. So since the point 0, 0 gave us a false statement when we plugged it into the inequality, that means we should shade the opposite section. 0, 0 was in the section below the curve, so we should shade this section. So that would be our answer for this equation, system of inequalities. Now, our previous example was not necessarily a system of inequalities because it was just a single inequality. The idea of a system of inequalities involves more than one. What we're going to do in this case is we're going to graph both equations as they would normally be, and then we're going to deal with the inequality part of it. Now, in both cases, it's easier to graph if it's in the terms y equals. So I'm going to manipulate the first equation, and notice if I subtract an x squared from both sides, I would get y is less than negative 5 minus x squared. This is a lot easier for us to understand intuitively than x squared plus y equals negative 5. We also had this equation. Now, just looking at these, I know this is dealing with a line, and this is dealing with a parabola. I know it's a parabola because the highest term is this x squared. I know this is a line because the highest term is x to the first power. I would say let's work on graphing the line first, and then we'll graph the parabola. And once we have it graphed, we'll deal with the inequalities. Now, both of these are not equal to, so they're going to be traced out with dotted lines and curves, not solid lines and curves. So for y equals 5x plus 10, I'm going to create an xy chart. I highly recommend this. Let's include values at like -2, -1, 0, 1, 2. And actually, I apologize, before we do this, it's important before we start picking what points we want to plot, we should first verify, do the curves ever intersect? The way we would know do the curves ever intersect is I'm going to turn these into two equations for now. Don't worry, we'll deal with the inequality part when it comes to shading at the end. But for now, I'm going to say consider this as the equation y equals negative 5 minus x squared. This will help us trace off the shape. And we need to know, do they intersect? Because thinking back to the beginning of our notes, we know that a line and a parabola could have no solution if they don't intersect, 1 or 2. So we need to set these equations equal to each other and solve to identify what case we're in here. Now here I already have y equals y. So this is one of the few cases where I could just set the equations equal to each other. 5x plus 10 equals y, but what else is y equal to? It's equal to negative 5 minus x squared. So these are truly the same if they ever intersect. And since there's an x squared, our hope here is probably going to be factoring, so let's move everything to one side. I'm going to add the x squared over. Now x squareds and x aren't like terms, so they don't combine. We can just leave it as x squared plus 5x plus 10 equals negative 5. Add 5 over to both sides. 0 equals x squared plus 5x plus 15. And now we need to think, do these equations ever equal 0? You might try factoring. Think if factoring works. So we'd want to think what integers multiply to give us 15 and add to give us 5. 1 and 15 doesn't work. 3 and 5 does not work. I can't think of any integers that multiply in this way to give us 5. So what I would do in this case is if I don't see a clear factoring, then I think I'd need to use the quadratic formula to verify if there's a solution. Now the quadratic formula is the solution to the parabola is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. If we apply the labeling where the constant multiple in front of the x squared is the a, the constant multiple in front of the x is the b, and the constant term is the c. Now in this case, since it's just x squared, there's an implied 1 times x squared, so a is 1. So we fill in the formula and we would get negative 5 plus or minus the square root of 5 squared minus 4 times 1 times c. Now our c is 15 all over 2 times 1. We'll simplify this term by term. That's 25 minus 60. And here we start to see issues, because whatever 25 minus 60 is, do we agree that's negative? And you can't square root a negative number. That takes you out of the real solutions. And we don't need to go any farther. This tells us that there are no real solutions. So this is the case where our parabola and our line, whatever they look like, they do not intersect. Because there is no real solution because you cannot square root a negative number. So back to our original question, do the lines intersect? No, they do not intersect. That helps us know what we're going to need to graph. So at this point, once you've verified if you're working with a system of inequalities, see if the equations of their own would intersect first. If they do, make note of the point that should be visible on your graph, but if they don't, then that helps us realize that we're just going to graph them over a reasonable range and we don't have to worry about any intersection point. So since we know they don't intersect, I don't have to worry about including their intersection, so I'm just going to graph. This is for y equals 5x plus 10. Maybe include points close to 0. I know at 0 I've got the y-intercept 10, and then the slope of 5 tells me I increase by 5 for each one that I go over, decrease by 5 for everywhere that I go back. And I think we should also get a table of values for our parabola around the similar x values, so -2, -1, 0, 1, and then 2. -5 minus 0 squared, that's just equal to -5. Similarly, plug in each of these x values in for x. -5 minus 4, that's going to be -9. Then we would get -6. -5, continuing to substitute, we would get -6 again. Substituting again, we would get -9. When we substitute each of these x values into the equation. Now that we have both equations plotted out, we will begin to graph it on the same axis. Let's graph our line first. Again, since it's strictly greater than, we're going to do a dotted line, but we'll plot a few points first. I'm going to draw this one in black. 5, 10, 15, 20. This is not necessarily going to be to scale. And then we would get the line. Now notice as we draw the line, it splits our coordinate plane into two sections. That's above the line, and that is below the line. And normally we would shade one of these based on the inequality and we'd be done. Since it's greater than, we would shade that's above. But since we have the other term, we still have to graph it as well and then coordinate both of them. So now let's plot the points for our parabola. We know at 0 it's at -5. And then we've got about -10. -9 is here. -6. Now we know this is a parabola, and again, since it is strictly less than, we're going to do a dotted line. And where this comes as a system is you shade both inequalities as they're stated, and you look for any overlap. If there's overlap, the overlap is the solution to the entire system. And if there's no overlap, then there's no solution. So specifically, since y is less than the parabola, we should shade below the parabola. So that's where we would shade for this part. Keep that focused in your mind. But the line has us being greater than the line. So here we are on the line, and if we want to be greater, then the y value should be above that, which means we would shade above the line, which would look like everything greater than the line. So we've shaded them both individually in our minds, and then we think about, do they ever overlap? Because only the overlapping portion would be the solution to the system. These are the shaded inequalities separately, but a system of equation asks you to look to see if they ever overlap. And since there is no overlap, nothing here is a part of anything here. There's no overlap, so we would say the solution is that there is no solution, because there's no overlap to where they're shaded. So our answer for this problem would be no solution.